In this video, we'll discuss differences in statistical power and type 1 errors between the parametric t-test and the nonparametric Wilcoxon Mann Whitney test. We'll first discuss the type 1 error and how it differs between the t-test and the Wilcoxon Mann Whitney test, also known as the Whitney U test or the Wilcoxon rank sum test. Then we will compare the statistical power between the two tests. Finally, we will compare the tests again, where we instead have a skewed distribution, and discuss some R code if you like to reproduce the results shown in this video, or if you would like to further explore the topic. To analyze the difference in type 1 errors between the unpaired t-test and the Wilcoxon Mann Whitney test, we will here consider the following simple example. Suppose that populations A and B represent the height of people living in two different populations that are normally distributed. One has measured the body height of all individuals in the two populations, which means that we know the population mean body height. In this example, the mean body heights of the two populations are exactly the same. This means that we in this example know that the null hypothesis is true, because the null hypothesis states that the two population means are equal. We therefore know that the alternative hypothesis is false, because the alternative hypothesis states that there is a difference between the mean body heights in the two populations. Now, suppose that we would select 5 random individuals from population A and 5 random individuals from population B. We measure their body heights and calculate the means of the two samples. We then compute p-values from both the t-test and the Wilcoxon Mann Whitney test. Since both p-values are greater than the general significance level of 0.05, none of the tests will reject the null hypothesis, which means that we will here draw the correct conclusion that there is no difference in the mean body heights between the two populations. Now, suppose that we would take a new sample. Due to chance, we now happened to select 5 quite tall individuals from population A and 5 quite short individuals from population B. As before, we measure their body heights and calculate the mean body height of the two samples. This time, both tests result in p-values that are less than 0.05. Because there was, due to chance, a big difference in the means between the two groups, which means that we would make the mistake of rejecting a true null hypothesis. This means that we have committed a type 1 error. Now, suppose that we would repeat this process 100,000 times, which means that we take a sample of 5 individuals from each population 100,000 times, and compute 100,000 t-tests and 100,000 Wilcoxon Mann Whitney tests, which means that we will generate 100,000 p-values from each test. Then we calculate the proportion of p-values that are less than 0.05. We see that about 5% of the p-values from the 100,000 t-tests are less than 0.05. This means that the risk of committing a type 1 error is about 5%. The Wilcoxon Mann Whitney test results in a bit lower risk. If we would repeat the whole thing again, but with a sample size of 10, we see that the risk is about 5% for both tests. The risk stays around 5% for both tests if we increase the sample size. This is expected because the risk that we have committed a type 1 error should be less than or equal to the significance level that we have used. Since we use a significance level of 5% in this example, the risk that we commit a type 1 error is expected to be equal to or less than 5%. Suppose that we, in this example, know that the people in population A are generally taller than the ones in population B. The mean height of the individuals in population A is 170 centimeters, whereas the mean height of the ones in population B is 160 centimeters. In this example, we therefore know that the null hypothesis is false, and that the alternative hypothesis is true, because the mean body height in population A is different from the one in population B. Same as before, we select 5 random individuals from population A and 5 random individuals from population B. Note that the 2 samples are representative samples in this case, because the observations are spread around the population means. We then measure their body heights and compute the p-values of the t-test and the Wilcoxon Mann Whitney test. Since both p-values are less than 0.05, we correctly reject the false null hypothesis with both tests. However, suppose that we now happen to pick 5 individuals from population A that were relatively short, and 5 individuals from population B that were relatively tall. Due to chance, the individuals from population A and B therefore happened to have about the same body heights. We now see that both p-values are greater than 0.05, which means that we incorrectly do not reject the false null hypothesis. We will therefore make a type 2 error because we did not reject the false null hypothesis. We will now have a look at the statistical power. The power of a test is defined as the probability that we will reject the null hypothesis given that it is false. The power of a test is therefore the probability that we will not commit a type 2 error. The power is therefore equal to 1 minus the probability that we commit a type 2 error. The statistical power depends on 4 things. If we reduce the significance level to reduce the risk of committing a type 1 error, we will increase the risk of a type 2 error, which means that we reduce the statistical power. By increasing the sample size, we will increase the statistical power. If the difference between the 2 population means is large, we will also increase the statistical power. For example, if there is a large difference between the 2 population means, it will be easier to identify a difference with the statistical test. Similarly, a smaller standard deviation in the populations will result in less overlap between the groups, which means that it will be easier to identify a difference. This will increase the statistical power. If we divide the absolute difference between the 2 population means by the standard deviation, we will get the so-called effect size. A larger effect size will increase the statistical power. Similar to before, we take 100,000 samples with a size of 5 from each population, which are normally distributed. The effect size is here 0.3, which means that there is quite much overlap between the 2 populations. We then compute 100,000 t-tests and 100,000 Wilcoxon Mann Whitney tests and check how many of the generated p-values that are less than 0.05. With an effect size of 0.3, a sample size of 5 and a significance level of 0.05, we see that the statistical power is only 7% if you use a t-test and only 5% if you use a Wilcoxon Mann Whitney test. This means that we only reject the false null hypothesis in 7% or 5% of the cases. The risk that we make a type 2 error is therefore 93% with the t-test and 95% with the Wilcoxon Mann Whitney test. By increasing the sample size, we see that the power increases. This is one reason why we should use a large sample size, because we like to have as high statistical power as possible. We see that the t-test has a bit higher statistical power than the Wilcoxon Mann Whitney test, but the difference is only minor. Suppose that we now increase the effect size to 0.5, which means that there is less overlap between the 2 populations. For example, with an effect size of 0.5, the power will increase from 10% to 18%. With an even larger effect size, we will approach a statistical power of 100%. The difference in statistical power between the t-test and the Wilcoxon Mann Whitney test is now quite high. For certain sample sizes, the difference in power is as much as 10%. Based on this simple analysis, we can draw the conclusion that we will get a higher statistical power if we use a t-test compared to if we use the Wilcoxon Mann Whitney test. Suppose that we would repeat the whole analysis, but this time use an unequal sample size of the two groups. For example, we here take a sample size of 5 from population A and a sample size of 8 from population B. An unequal sample size will actually result in a smaller difference between the t-test and the Wilcoxon Mann Whitney test. By using an unequal sample size, the risk for a type 1 error still stays around 5%. In summary, we can conclude that the t-test has a bit higher statistical power than the Wilcoxon Mann Whitney test when the data is normally distributed. We'll now repeat the whole thing again, but we will this time use a skew distribution. As an example, I will here use the log normal distribution. Similar to before, we'll try different effect sizes, which means that we will shift the distributions so that there is less overlap. We can again see that the power increases with a larger sample size. What is interesting is that the Wilcoxon Mann Whitney test now has a larger statistical power than the t-test. If we increase the difference between the two distributions, we see that the Wilcoxon Mann Whitney test has a much higher power for certain sample sizes. The difference can be up to 20%. In summary, we can conclude that the Wilcoxon Mann Whitney test has a bit higher statistical power than the t-test when we sample from a log normal distribution. Generally speaking, the Wilcoxon Mann Whitney test usually has a bit higher statistical power than the t-test when the data is highly skewed. The type 1 error stays below 5% for both tests when we use a log normal distribution. Finally, I will show some simple R code that you can use to reproduce the results shown in this video. We set k to 100,000, which defines how many tests that we will compute. On my computer, it takes about 1 minute to run 100,000 tests. You might want to reduce this value to 5,000 to reduce the simulation time. In this example, we will use a sample size of 5. We then initialize two vectors where we'll save all the 100,000 p-values. Next, we'll create a loop, which means that this piece of code will be repeated k number of times, which in this example means that it will be repeated 100,000 times. In every iteration, we draw 5 random numbers from a normal distribution, with a mean of 0 and a standard deviation of 1. We also draw 5 numbers from a normal distribution with a mean of 0.3, which in this example means that the effect size is 0.3. Then we compute a t-test and a Wilcoxon Mann Whitney test based on these 10 random numbers and save the extracted p-values in the two vectors. Note that we here use the classical t-test, which assumes equal variance. By default, the Wilcoxon Mann Whitney test in R computes exact p-values. Finally, we sum how many p-values from the t-test that are less than 0.05 and divide by k, so we get the proportion of p-values that are less than 0.05. Then we print the percentage of p-values that are less than 0.05 with 2 decimal places. Finally, we do the same for the Wilcoxon Mann Whitney test. To use a log normal distribution, we instead use the function RLNorm. To increase the effect size, we simply increase this value. And to increase the sample size, we simply increase this value. To run simulations where the null hypothesis is true, we use the exact same mean values. You might even try simulations where the two samples have different standard deviations, where you instead can run the Welch t-test by setting this argument to false. If you find other interesting differences between the two tests, please place a comment below to share your findings. Note that every time you run this code, you will get a bit different result because it is based on random numbers. Note that we can also compute the exact statistical power of the t-test based on equations by using the following package. If you run this code, you will get a power of about 7%, which will approximately correspond to the stochastic simulations with the following code, given that we run a large number of iterations. This was the end of this video. Thanks for watching.